Welcome back to the course real time digital signal processing. So, we are continuing with the IIR filter. Today we will see that quantization and then how it is going to affect our design basically. As a recap, we have been discussing from past two lectures IIR filters. You know how it is going to have effect on the quantization and then how to design it, why we have chosen IIR filter and then compared to FIR filter. Except linear phase, we are going to have few number of filters coefficient which is going to be designed. So, that is the advantage of it, and then we know that most of the earlier work goes on using analog filters. So, we will see what are the quantization values what we are going to get. It's here it is going to show me h of n. So, you will be seeing the FIR filter continuous signal. The values which are represented is minus 1.10 power minus 4 to, you will be seeing that some more values are present. So, when I do the quantization of it, what we call it as HQ of n quantized thing. So, you will be seeing a threshold what we will be putting, these are the values which are not going to be represented. So, you will be seeing up to some of the very low values which are going to become 0, then rest of it are going to be quantized to certain values. So, you will be seeing in the end also. So, some of the coefficients are made 0 although they have the values. So, this is the quantization what it is going to happen. So, in the FIR filter. So, how the response is going to be, we will see it in a while. So, you will be seeing that the black representation shows that this is the frequency response with respect to magnitude. So, you will be seeing based on the quantization which is shown in the dotted lines. So, you will be seeing that my cutoff frequency or stop band just gets moved up. So, from minus whatever it is around greater than minus 80 dB. So, which will be dropped down to around minus 40 or 30, it is in the range minus 30 to 40 dB. So, this is the coefficient quantization. So, one has to consider when we are doing using in the hardware. So, our design has to account for this quantization effects. So, coming to the this thing, this is the passband region what it has been taken. So, you will be seeing how it is going to be represented. This is in the terms of magnitude and this is in frequency in kilohertz. So, this is black one shows are unquantized and then the dotted lines it shows that it is the quantized. So, here I am supposed to get a flat response. So, where what is the thing is happening? So, there is a ripple in my passband in the representation. So, these are the effects one has to consider. So, what is the thing is going to happen with this quantization? So, we will see the effects of it. So, whatever we have h of n, if it is unquantized then output is going to be normal. So, if there is an error because of the thing, so which is going to be added with respect to that. So, output will be my impulse response coefficients what I will be getting it. So, in terms of frequency domain, we know that h of n is going to be represented as h of omega and then our error function is represented as E of omega. So, output will be quantized basically HQ of omega what will be the response of the filter. So, how it is going to affect we will see in this block diagram, that is basically dynamic range and accuracy requirement of different applications one needs it. So, we know that in noise cancelling, so dynamic range in number of bits what we will be telling 32 bits what we need it. So, whereas accuracy it is 20 bits is enough, whereas in the radar processing it is 32 and then same thing 20 bits, whereas in case of broadcast quality picture processing. So, both what we need is 20 bits. So, we see in the image processing it is 30 and 20. So, medical spectrum analysis, if you are doing it, both can have 20. So, when you are going for the seismic data processing, you will be seeing that the dynamic range what we need it 70 bits to 20 bits. So, most of the cases whatever we are designing 6713 DSK board, what we are using it, which is 16 bit. So, almost it is nearer to the thing what we can have. So, coming to quantization, so all of us know that what we have to do is because most of the signal in nature is analog in nature. So, we represent it analog input as x of t. So, if I want to do what is it band limit the signal, so I have to pass it through the low pass filter. So, we call this as a anti-aliasing filter also. So, that will be limiting the stop band frequencies which are going to creep in. Most of the stop band frequencies we say higher the frequencies are the noise. So, we are limiting it and then we will be feeding it into our sample and hold circuit. So, when it is closed you will be seeing that more than whatever the value of it. So, we will be getting the output, sample and hold circuit is going to work. Then we are going to do the quantization. So, we know that depends on number of bits. So, the representation will be 0 to 2 to the power of n minus 1, n is the number of bits ADC circuit what it is going to have. So, we have to do the encoding of this number, we use a logic circuit to do the thing, and x of n will be our digital output coming out of our ADC. So, we have seen the different structures. Here we are going to see that this is my direct form 2 what we derived it in the last class. So, what are the coefficients for it is B0, B1, B2 and A1 and A2, and then x of n, y of n, w of n and then w of n minus w of n minus 2. So, these are the parameters what I have to store it. So, when I see the direct form 1 structure, so we will be seeing that this is zeros are in the feed forward, whereas poles are in the feed backward stages. So, you will be seeing that I need so many coefficients to coefficients are 5 in this case also, except that we need y of n minus 1, y of n minus 2 output also in the case of it. So, that is 3 plus 2 5, but we need output to be fed back into the system. Whereas, as we can see here I have one adder as I have discussed in the last class also. The quantization effect may nullify sometimes here, whereas in this case it may little bit override. So, that is the representation. We have y of n is as we know about it, it is b naught into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2 minus a1 into y of n minus 1 minus a2 into y of n minus 2. So, in both the cases it is the same, but the delay elements here what we need is 4 delays, whereas in this case it becomes only 2 delays in the case. So, that is the reason why most of the applications use direct form 2 structure compared to direct form 1 structure. So, now we have to see that when we have taken the direct form 2, so how the coefficients are going to be represented, whether they are going to cause any instability. So, we will be seeing that it is the coefficient values for a stable second order IIR filter. So, what should be the region of it? So, we say this is our coefficients A1 and then A2 what we are representing. Most of the time it is the poles which are going to have instability for the filter. So, we will be considering A1 and then A2 coefficients what we have plotted. So, we call this is the triangle which is going to be represented. So, we know that 1 is maximum and then -1 in this, and then we will be having 2 for A1 and -2. So, the rest of the thing represented minus A1 will be, this is equal to 1 plus A2 this location, and then this is A1 is equal to 1 plus A2. So, how we have arrived at this is shown with the poles here. So, we consider the feed backward section and then analyze it. So, what we have is 1 plus A1 into Z minus 1 plus A2 into Z minus 2, which is nothing but 1 minus P1 into Z minus 1 into 1 minus P2 into Z minus 1. So, we represent A1 is equal to P1 plus P2 and A2 will be P1 into P2. So, we see that poles must lie inside the unit circle for our stability. So, that means that magnitude of P1 should be less than 1 and magnitude of P2 should be less than 1 in this case. So, magnitude of P2 also has to be 1. Then what happens, magnitude of A2, what it is given by magnitude of P1 into P2. So, which is less than 1. So, A1 as you can see it is 1 plus A2. So, it will be magnitude of it can go up to 2. That is what we get it from this triangle. This is how it has been plotted. So, coming to the advantages of cascade section, we will see with an example here. So, impulse response of the filter in Z domain is given as h of z is equal to 1 by 1 minus 0.9 z minus 1 plus 0.2 z minus 2. So, if we consider the pole, then what happens, z is equal to 0.4 and z is equal to 0.5. So, in the cascade form representation, we represent this as h1 of z into h2 of z. So, what is it? We will be having h1 of z is nothing but, so 1 by 1 minus 0.4 z minus 1, and then h2 of z is going to be 1 by 1 minus 0.5 z minus 1. So, actually this has been converted into 1 minus 0.4 z minus 1 into 1 minus 0.5 z minus 1 will realize this equation. That is how the poles are there. So, if we say that I am going to represent it with 4 bits, you have to call back our number system, then what happens? So, we have to represent all these values, we will see in a while, that is 0.9, 0.2, 0.4 and 0.5. So, what is the nearest number I can represent with all these values? So, this is the direct form what I have taken, this is the second order section what we have taken the thing. So, 0.9 is represented as 0.875 and then 0.2 is represented as 0.125. So, in the case of 0.4 we will represent it as 0.375 and then 0.5 directly is represented as 0.5 in our fixed format. So, coming with the thing, so this is what we have done, the second cascade section. So, what happens to the pole locations? In the direct form, what we call it as, because this is the quantized values what we are going to represent it, h dash z is our z is equal to 0.1 and z is equal to 0.695. In the cascade form, what happens to our h dash of z? So, here it is going to be z is equal to 0.375 and then 0.5. So, you will be seeing that instead of what we are supposed to get is 0.4 and 0.5. So, in the direct form pole location is at 0.1 and 0.695. So, you will be seeing it they are very far apart, whereas in the cascade form you are seeing that they are nearer to whatever the values what we have represented. So, that is the reason why we use the cascade form compared to the direct form. So, you will be seeing that the poles are nearer. The poles cascade realizations are closer to the desired or impulse response in the Z domain what it shows. So, now how because we are going to have many cascade sections, it is only second order one section what we have taken the thing. If we have multiple sections, how we are going to combine, because we will be arriving at poles and zeros. So, how we are going to combine them is shown by this diagram. That is, first what we do the thing, complex conjugate poles what we are considering here. So, they have been named as first conjugate pole here, and then the second set, and this is the third set. So, we say the closest to the unit circles. So, that is which is closer to unit circle is named as 1, responsible for the greater overshoot, are paired with complex conjugate zeros closer in frequency, that is angle on unit circle. So, we pair this one with this one. So, that is the reason why we have colored them. The first one which is shown with green is paired with this green, the next one is the blue. So, that is what it says. Then the process iterate with the next complex conjugate closest to the unit circle. So, this one with next zeros, and then one is nearer to the 0 is connected with the nearer to the pole of zeros. So, otherwise one has to do trial and error method, or you have to see how the pairing is going to happen, as we have seen in the last class. So, the quality factor, how it is going to affect our pairing also is one of the important aspect. So, this is one of the method what one can use, so that we may get a good pairing of poles and zeros in our cascade section. So, coming to the thing, as we know that direct form 1, we said that there is no overflow, it may or it may not have it, but definitely we have in the cascade section 2 adders which are coming in. So, because it is the same what magnitude what it is going to be added, or same sign magnitudes are going to be added. So, I may have a overflow or an underflow. So, to avoid this overflow and underflow, we have to have a scaling factor. So, you will be triggered with why did we choose a scaling thing, that is barrel shifter what we call it, either shift right or shift left, which is required for scaling my input also in this case. So, that is what it is shown here to prevent our overflow in storing at node W n. Okay. We need a scale factor to have a 0 dB gain from input to this node. This scale factor, what we call it as alpha k, is commonly computed depending on the nature of signal that will be processed. So, for narrowband signal, in this case we use the L infinity norm, then we get alpha 1 as 1 by norm of 1 by A of f, infinity norm what we are taking it. So, if we want to process the wideband signal, we usually use L2 norm. In that case, our alpha 2 scaling is going to be 1 by norm of L2 norm of 1 by AF input signal. So, furthermore we have alpha 2 greater than or equal to A1. Always this is at a higher this thing value compared to alpha 1 we are going to have the scaling. This is the maximum scaling what we can provide. So, how we are going to order? That is what we said, criteria for scale factor computation, we are going to have it as L infinity or L2 norm one way, one of the thing what we will be selecting it. So, which norm of the quantization noise we want to minimize, whether we want to L infinity, that is the maximum value, or L2 norm, that is the power which is going to be considered. So, these are the rules one has to apply. So, L infinity for scale factor and L2 for noise, that is we will be ordering the second order section ascending order of overshoot. So, when we have L2 for scale factor and L infinity for noise, then we will be having descending order of overshoot, what we have to look into the thing. Based on this, we will be organizing our second order section in ascending order or descending order depending on one of this. So, if the same norm is used, so there is no preferred order. So, you can go in whatever order you want to have it. So, what is the practical application of IIR filter? So, here we have considered Pi is our pole positions, which is given by Rp. So, R is the radius of the circle into e power plus or minus j omega naught. Omega naught is the angular frequency what we are considering. So, we assume that Rp is in the range 0 and then 1. So, the transfer function can be expressed in that case as we have h of z is equal to a divided by 1 minus Rp into e power j omega naught into z minus 1 into 1 minus Rp into e power plus or minus j omega naught z minus 1. So, when you this is my conjugate poles what I have taken the thing. So, we will be this is the second order sections what we are representing, this is the first one and this is the second one what we are multiplying it. So, then I expand the thing, it becomes a by 1 minus 2 cos omega naught z minus 1 plus Rp squared into z minus 2. So, we represent these values as A1 and then A2. So, what happens in the frequency domain? So, if we are considering the normalized filter, the magnitude response is given by that is we will be substituting z is equal to e power minus j omega naught in this equation. Then it becomes h of omega naught, magnitude of it is given by a divided by 1 minus Rp into e power j omega naught into j e power minus j omega naught, and then the second term what you will be getting it. So, this condition can be solved to obtain the gain, that is what is my A is equal to. So, the magnitude of this. So, some quantized values q minus Rp what we will be assuming it into 1 minus root of 1 minus 2 Rp into cos 2 omega naught plus Rp squared. So, how we can represent this? Okay. So, this is my magnitude A, x of n is the input, and then what I have is z minus 1 is the delay. So, the equation has in from the previous case what we are taking 2 Rp cos 2 omega naught here. So, that is what 2 Rp cos omega naught is represented as a coefficient, and this is my minus Rp squared is the other coefficient. So, which are fed into my adder and y of n is the output. So, we say that this is the signal flow graph of our second order section. So, what will be y of n if I consider this is the filter? As the name says it is a resonator filter, I will comment on it in a while. This is a into x of n minus a1 into y of n minus 1 minus a2 into y of n minus 2. So, where we have a1 is equal to minus 2 Rp cos omega naught t cos omega naught, and a2 is Rp squared. So, consider two causal impulse responses, that is Hc of n is given as cos omega that is the cos function what you have considered cos omega naught n into u of n. So, the second one I can consider it as a sine function, Hs of n is equal to sine omega naught into omega naught n into u of n. So, then the equation as you will be seeing that the cos function is given by this equation and then sine function is represented this way. Then what happens to my Yc of n is nothing but w of n minus cos omega naught into cos of into w of r n minus 1, and y as sine function is given as sine omega naught into w of n minus 1. So, where we say W of n is an internal state variable that is updated as using this equation, W of n is equal to cos 2 omega naught into W of n minus 1 minus W of n minus 2. So, coming to the resonator, so all of us know that infinite impulse response, why the name comes is, once I remove the input, I can remove the x of n. So, the system is going to oscillate on its own. So, what is the advantage of it? So, this resonating response, what we will be using it in our generating sine wave. So, we will see in the lab how we can giving only these 3 coordinates, as we know that sine function is represented using the table. You can do the thing, or we derived the harness way of representing it by expanding in series, or you can use the math function sine or cos function. All of us know that when we use these functions, it is going to take a long time to compute. So, with this IIR filter with 2 feedback, we know that we can calculate the amplitude with 2 input, because it is a LTI system. Usually we give initially 0, then automatically by giving x of n equal to 1. So, it automatically start resonating, and then we can generate different kinds of sine frequencies, and then we can use it in our sine generation. So, the next application is in the recursive quadrature oscillators. So, those who are comfortable with communication, you know where you need the quadrature oscillator. So, how we are going to generate this? So, you will be seeing this is a W of n and then W of n minus 1 in this case also. So, you will be seeing that 2 cos omega naught is the feedback signal what it is going, and then feed forward what we have is a multiplication with sine omega naught, and you will be seeing 2 delays. This is W n minus 2, which you will be subtracting with the thing, and you will be getting your cos, and then here you will be getting the sine. So, how you are going to get it? So, you will be seeing that y s of n is nothing but a into x of n. So, that is what you are getting the thing, minus a 1 into y s of n minus 1 minus a 2 into y s of n minus 2, which is nothing but, if you simplify it, it is going to be 2 cos omega naught y s of n minus 1 minus y s of n minus 2. So, with the initial conditions, y s of 1 is equal to a sin omega naught and y s of 0 is equal to 0, then I can calculate the frequency of it as cos inverse my magnitude of a 1 by 2 into f s by 2 pi into in terms of hertz. This is the frequency what I will be generating it, where the coefficient magnitude of a 1 should be less than or equal to 2, which we got it in our triangular representation. Okay. So, this completes our IIR filter for with respect to structure, and then what is the quantization effect. So, we will be solving some of the problems how our center frequency is going to change with quantization. So, without quantization with number of bits that is represented. So, we will be seeing in our next class. Thank you. Happy learning in this class.